Mathematics is an integral part of physical chemistry and science in general. Today's goal is to learn selected topics needed to deal with mathematics used in thermodynamics, which is a major part of physical chemistry. The complexity level of mathematics presented here ranges from very basic to a fairly medium level. Topics include numbers, scientific notations, units of physical quantities, graphs, differentiation, integration, sequences and series. Complete video lecture consists of few parts. Current part contains basic concepts of maths and graphical representations of chemistry phenomena. First thing in mathematics is, of course, numbers. Numbers are of different kinds. They are usually classified as different sets. Set is represented in curly braces. It can include a finite or an infinite range of numbers or other terms. A set that has only zero or does not have any term is called a null set. Conventionally, a kind of number is denoted by an alphabet written in a unique font. I have used Castella from MS Office. The most familiar kind of numbers is the natural numbers. They are used in our everyday life, for example, in counting. Natural numbers are represented by letter n equals to 1, 2, 3, ... 3 dots at the end means that set continues forever. Whole numbers, denoted by W, are natural numbers but also include 0. So whole numbers are 0, 1, 2, 3 and so on. Integers are all the whole numbers and they also include the negatives of the whole numbers. Integers, denoted by Z, are equal to ... -3, -2, -1, 0, 1, 2, 3 and so on. A line plotted with integers can also be called a number line as shown here. The next one is rational numbers, which are denoted by Q. These are positive or negative fractions, which are easy to grasp. Random examples are 0.6, 1/2, 3/8, 6/1, and 5/4. Irrational numbers, denoted by F, are a little strange. They are continuously expanding numbers. Examples are pi, which is equal to 3.1428571 ... and square root of 2 is equal to 1.41421356 ... Prime numbers are among the natural numbers that cannot be factorized or written as a product of whole numbers without using 1. These are denoted by P, and their set is P equals 1, 2, 3, 5, 7, 11, 13, 17, and so on. Compound or composite numbers are the natural numbers that can be factorized without using 1. There seem to be no letter assigned to denote them. Let's denote them with D. Set of compound numbers include 4, 6, 8, 9, 10, 12, 14, 15, and so on. Real numbers include all the kinds of numbers mentioned above. They are denoted by letter. Examples from the line of real numbers are -5, -pi, -1/2, 0, 1, 2, 3, square root of 2, 5, etc. Such a number line with -half on left, +half on right and a 0 in the middle includes all the numbers, either whole or fraction, or positive or negative numbers. There is another kind of numbers that do not fall under the category of real numbers. These numbers are called imaginary numbers, denoted by I. All imaginary numbers have a factor of square root of -1, denoted by small italic I. This cannot be solved any further. Examples of imaginary number are -root of -1, 0, root of -1, root of 4 minus, cubic root of -1, 2 plus cubic root of -1. The line of imaginary numbers is actually perpendicular to the line of real numbers. Therefore, 0 is both a real and an imaginary number. How beautiful is that? At last, there are numbers that include both a real part and an imaginary part, hence are called complex numbers. They are denoted by C. Examples of complex numbers are a plus bi, c minus di, and x plus yi, a plus square root -1. You will see that these numbers are very important in quantum chemistry. The solution of complex numbers is achieved by applying basic arithmetic operations. If Z is a complex number, it can be solved by multiplying it with its conjugate complex. A conjugate complex, denoted by an asterisk on its top right, is the same as its original number, except the sign of the imaginary part is changed to opposite of its original sign. The product of both will result into solvable number. their product will be z into z asterisk equals a plus bi into a minus bi, which is equal to a squared minus b squared I squared. This turns out equal to b a squared plus b squared. This process has helped to eliminate imaginary part. Numbers can be classified into more kinds, but the ones that have been discussed are sufficient to meet our needs. Now, let's review some arithmetic operations as well. Suppose a, b and c are numbers. The product of two positive numbers will be a positive product, but if any one of the two numbers are negative, their product will be a negative number. The product of a and b will be equal to b and a. A multiplied by b into c will be equal to a into b multiplied by c. A multiplied by the sum of b and c is equal to the sum of a into b and a into c. In mathematics, any number, or any other thing, with power 0 is equal to 1, for example, a power 0, y power 0, x plus y squared whole power 0, 1 million power 0 are all equal to 1. On the other hand, any number with power equal to 1 is same as the number. That's why power 1 is usually not written. Regarding division, b over b is 1, b squared over b equals b, and minus c over c equals minus 1. When a number is multiplied by itself, its powers are summed up. Examples are a power x into a power y equals a power x plus y, c into c equals c squared. That's why 10 to power 3 is 10 into 10 into 10. Negative power of a number represents the inverse of a number. b to power minus 1 is equal to 1 over b, b to power minus 3 equals 1 over b cubed, and 1 over c to power minus 3 equals c cubed. Root number is the inverse power of number. Cubic root of b equals b to power 1 over 3. Quartic root of c equals c to power 1 over 4. And square root of b equals b power 1 over 2. Enough has been learned about numbers. Letters are also used to denote numbers, as we just did. Numbers are constant, they do not change their values. Unlike numbers, there are terms that change their values, called variables. Suppose an equation that says x equals 2 plus n, where n is a set of natural numbers 1, 2, 3, and so on. In this equation, n is a variable, 2 is a constant, and x is another variable that depends on n. This equation is also a function. Functions will be discussed later. Now, let's learn the units of physical quantities used in physical chemistry. The units are necessary to describe things properly. There could be several measurement systems of physical quantities, which makes use of units necessary. For example, 40 degrees of temperature with wrong units could be lethal. Another example would be the measurement of distance. Distance is measured in yards, kilometers, and miles. International System of Units, SI, is the most widely accepted standard. Organization's real name is in French language, that is why we see and hear SI units, not IS units. There are 7 original SI units. And then, there are other units which are derived from the original SI units. First one is kilogram, which is a unit of mass, abbreviated as kg. Second one is meter, m, the unit of distance. Time is expressed in seconds. Temperature is measured in Kelvin, abbreviated as K. Kelvin scale is also called a thermodynamic scale of temperature. The amount of a substance is expressed in moles, written as mol. Electric current has units of ampere. And the last one is luminous intensity measured in candela, which is abbreviated as CD. The derived SI units include the following. Force F is measured in newtons. F equals ma. Its derived units from the original SI units are kilogram meter per second squared. Second quantity with derived units is pressure. Pressure is the force per area. Its SI units are Pascal, which is equal to Newton meter squared by definition. In SI units, pressure is expressed as pascals, that is equal to kilogram per meter per second squared. Energy is measured as joules, J, which is equal to 1 kilogram meter squared per second squared. Volume is a distance in 3 dimensions. Its SI units would be in cubic meters. It is also measured in cubic centimeters, which is written in 2 ways as shown here. SI unit of electrical charge is coulomb. 1 coulomb is equal to ampere second. Next one is magnetic field. Its SI units at Tesla equal to kilogram per second squared per ampere. Luminous flux has units of lumen, which are equal to candelas to radian. Scientific notation is an expression of writing numbers in a short form. They are quite useful in many fields because numbers can be very small as well as very large. They both can be too hectic to write as whole. For example, charge on a proton is 0.0000000000000000000000 or 1600218 coulomb, but using scientific notation, it can be written as 1.60218 by 10 raised to power minus 19 coulomb. The speed of light is roughly 300 million meter per second, but it can be written as 3 into 10 to power 8 meter per second. The scientific notations are also useful while performing the interconversions between bigger and smaller units. It would be useful to perform some conversions of units using scientific notations. But before that, let's get familiar with the scientific notations of small units of meter. 1 decimeter is equal to 1/10 of a meter, 1/10, which can also be written as 10 raised to minus 1. Similarly, centimeter is equal to 1/100th of a meter and can be written as 10 raised to power minus 2, and so on. Millimeter equals 1,000th of a meter, micrometer equals 1/1,000,000th of a meter, and 1 nanometer equals 1/1000,000th of a meter. Meaning, inverse of nano would be 1 billion. There are many ways to convert units from smaller to bigger and bigger to smaller. The best way is to choose one method, which is easy for you, even if it takes longer time. Just by practicing, you will be fast in that seemingly long process too. When doing it without calculator, first replace the symbol of a unit to be changed with its value, then solve the number part. For example, a number A equals 2.7 into 10 raised to power minus 4 millimeter, and it is needed to be expressed in meters only. First thing is to replace milli with its value, which is 10 raised to power minus 3. It will give A equals 2.7 into 10 to power minus 4 into 10 to power minus 3 meters. By solving the magnitude part, A equals 2.7 into 10 to power minus 7 meters. Thus, 2.7 into 10 raised to power minus 4 millimeters equals 2.7 into 10 to power minus 7 meters. Any of the above can be converted into smaller units as well. For example, if one wants to write 2.7 into 10 raised to power minus 4 millimeters into nanometers. Again, first, milli is unwanted here, so it will be replaced by its value. And A would be equal to 2.7 into 10 raised to power minus 4 into 10 raised to power minus 3 meters. In the next step, write the word nano before meter, and also write the inverse of the value of nano to keep things balanced. Then, A in nanometers will be equal to 2.7 into 10 to power minus 4 into 10 to power minus 3 into 10 to power plus 9 nanometers. By solving, we get 2.7 into 10 to power 2 nanometers, or 270 nanometers. Remember, when unit becomes smaller, number becomes larger, and vice versa. The value remains the same though. It becomes little tricky when units of volume are interconverted, because third dimension has been added. But, following the steps thoroughly help avoiding mistakes. For example, if 1.8 into 10 to power minus 4 cubic centimeters is desired to be converted into cubic millimeters, the first thing is to replace the value of cubic centi. We get V equals 1.8 into 10 to power minus 4 into 10 to power minus 2 whole cubed, m cubed, then whole cube of centimeter will be equal to 10 to power minus 6 cubic meters. Therefore, V equals 1.8 into 10 to power minus 10 cubic meters. Now, inserting cubic milli and its inverse before units. Cubic milli is equal to the cube of milli, and its inverse will be 10 to power 9. Then, volume will be equal to 1.8 into 10 to power minus 10 into 10 to power 9, which then will be equal to 1.8 into 10 to power minus 1 cubic millimeter, or equal to 0.18 cubic millimeters. There will also be a frequent need of unit conversions for other quantities, which we will learn along the way. Graphs are always used in physical chemistry. Graphs are quite useful because they give a descriptive image of the behavior of the properties of matter. Many properties and relationships can be observed from a graph. Most commonly plotted graphs are of two dimensions, the horizontal axis and vertical axis. Conventionally, two-dimensional graphs have an independent variable and a dependent variable. Data points of one variable are plotted along one dimension and points of another variable along other dimension. For example, the age of boys is an independent variable and what grade or class they study is the dependent variable. Of course, there can be some anomalies, but it is assumed that there are no anomalies. This data can also be used to interpolate as well as extrapolate new data points. Interpolate means predicting the unknown data points within the given range of data, and extrapolate means predicting the unknown data points beyond the given range of data. Another example, which is directly related to thermodynamics, is the graph of temperature and volume of a gas. The container of the gas has a movable piston. The temperature here is an independent variable, and volume of gas depends on temperature. If the temperature is increased, the gas will expand and will occupy greater volume. The ratio of the change in vertical axis to the change in horizontal axis is called the slope of the line. In this case, the ratio of the change in volume to the change in temperature gives a parameter of the system called constant of proportionality, K. In this way, graphs help to find many properties related to the variables plotted in graphs. Another very important graph is a graph of potential energy of molecular systems against the distance between atoms. The potential energy is present due to the electrostatic attraction and repulsion among the nuclei and electrons of atoms. When atoms are too close, the potential energy will be high due to high repulsion, and when the atoms are too far apart, potential energy curve will form well-shaped curve. The bond between the atoms will eventually break. Somewhere between these two scenarios, there will be a point of distance between the atoms where both atoms are most stable. That is the point where potential energy is minimum and the distance is called equilibrium bond length. This graph is also drawn in 3 dimensions and the resulting plot is called potential energy surface. Many crucial properties of molecular systems are deduced from these curves.